Hello, my name is Misbah, and this is my presentation on password strength analysis using counting principles. We all create passwords every day, but what actually makes a password strong? Today, I will explain how counting principles measure password strength. Even though we create passwords every day, many people still use weak passwords like 1234566 password ABC123. The issue with this is that these passwords are very easy for attackers to guess. So, what makes these passwords weak compared to others? To understand that, we use something called the product rule. The product rule is a counting principle that states that if you have a task that can be broken into a sequence of steps, and step 1 has n1 ways, and step 2 has n2 ways, and so on, then the total number of ways to complete the task is n1 times n2. So to put this into example, if you have 3 shirts and 2 pair of pants, how many outfits could you possibly make? All you have to do is just multiply 3 times 2 to give you 6 outfits. Because for each shirt, you can pair it with every pair of pants. And passwords work the same way. Each character in a password is a choice, and we multiply the number of choices for each position. We can generalize this idea with a formula: n equals k to the power of n. Here, k is the number of possible characters and n is the length of the password. For example, suppose that we have a 4-digit PIN and each digit can be from 0 to 9 with repeats. In this case, k would equal to 10 and n would equal to 4. So we would get 10 to the 4th power, which would give us 10,000 possible combinations. This basically means that attackers would need to try up to 10,000 combinations to try and crack your password. So a small n or a small k would equal a small number of possible combinations, which would lead to a weak password. If we only use digits, we have 10 choices. If we use lowercase letters, that gives us 26 choices. If we use uppercase plus lowercase, that gives us 52 choices. And if we add numbers to that, we get 62 choices. And if we include symbols, that would bring it to about 94 choices. So every time we add more types of characters, we increase k, which increases the total number of possible passwords, making a stronger password. Now we will see how quickly the number of possible passwords grows when we increase the length. As I've mentioned before, a 4-digit PIN has 10 to the 4th power, which equals to 10,000 possible combinations. But a 6-digit PIN has 10 to the 6th power, which equals a million possible combinations. By adding just 2 more digits, the number of possibilities becomes 100 times larger. This happens because each additional digit multiplies the total number of combinations. So even a small increase in password length can make a very big difference in security. Let's compare 2 8-character passwords. One uses only lowercase letters and has 26 to the 8th power possible combinations, which is about 208 billion possibilities. And the other one uses all characters, including uppercase letters, lowercase letters, numbers, and symbols. Here we have 94 to the 8th power possible combinations, which is about 6 quadrillion possibilities. Even though both passwords are the same length, the one with more character choices is much stronger. That's why adding special character and symbols help. So, which is stronger? The length of a password or the complexity of it? A short password using all types of characters or a long password using only one type of characters? Well, if you look at an 8-character password that uses all types of characters, you can see that it has a K of 94. It has a K of 94, and it gives about 6 quadrillion possible combinations. And if you look at a 12-character password with using only lowercase letters, it has a K of 26, which gives about 95 quadrillion possible combinations. So the longer password is actually stronger, even though it uses only lowercase characters. This happens because increasing the length, which is n, has a greater impact than increasing the number of character choices, because n grows faster than k. To measure password strength, we use something called entropy. Entropy is a quantitative measure in bits that measures the uncertainty of a password, indicating how many guesses it would take an attacker to crack it. High entropy means more randomness of characters and longer lengths and a greater resistance to hacking. The formula for entropy is log of n, where n is the total number of possible passwords. Each bit doubles the number of possibilities. A password with 1 bit of entropy has 2 possibilities. 2 bits has 4 possibilities. 10 bits has 1,000 possibilities, and so on. So if we go back to our 4-digit PIN example, 10,000 total possibilities. So if you plug that into log of 10,000, that's about 13.3 bits. That's very tiny. An attacker can try all 13.3 bits worth of possibilities very quickly. A strong password should have 60 to 80 bits of entropy. I'm sure you have seen a lot of websites. When you're making a password, they require a lot of things. They require an uppercase letter, a lowercase letter, a number, a symbol, and must be a minimum of 8 characters or so. These rules are designed to increase the number of possible combinations. By increasing both the length and a variety of characters, the total number of possible passwords become much larger. This makes it much harder for attackers to guess the correct password. To conclude, this entire presentation is based on discrete mathematics, specifically the product rule, which is one of the fundamental counting principles. We use this idea to build the formula k to the power of n, which allows us to calculate the total number of possible passwords. From this, we learned that password strength is directly related to the number of possible combinations. We also saw that increasing the length of a password has a greater effect on security than just increasing complexity, because it increases the exponents in the formula. Therefore, we can conclude that password strength is not just a computer science idea, it is a real-world application of discrete mathematics.